Thank you. You're welcome.
Good morning. I'm excited to be here. I'm excited because I get a chance to talk to you about digitalization. 2 weeks ago, we were in Russia. We had, 800 to 1,000 people show up at the Russian Users Conference. Thursday, I was in China. We had over 5,000 people at the conference. And I think the reason so many people are showing up is they want to hear about this idea of digitalization and what innovation capabilities that we bring to them to be able to change and think about the way they run their business. So I hope there's value that we can bring to you there this week as well and what we have to show you, because we have a lot to show you to talk about what we're doing in this space. When you think about the business of innovation, really all of us are having to deal with this. We're either testing, we're implementing, we're doing something to think about what comes next, right? And what comes next could be something like designing the next tennis shoe. It could be that I've got to design the factory of the future, where Adidas is working with us. I say Adidas for my German friends, Adidas, working with us to figure out how they build lot size 1, individualized tennis shoes. And how do you make a factory do that? It could be that you've changed your complete business model, leveraging IoT to where you sell service rather than your product to the industry. So all different levels of innovation. But what we see is sometimes we throw technology at the problem. We think we've got a cool new widget, some new idea, and it's going to solve all of our business issues for us. And you think about the computer age. Think about where we're at today. Is there anything that's impacted us more than what's transformed our way of working over the last 20 years in the computer age? Yet this guy, Robert Solow, in 1987, said you can see the computer age everywhere, but you don't see it in the productivity statistics that are there. He had this paradox he described. He said, the dividends of productivity enhancing disruptive technology were reaped slowly, with an initial lag, due to the time it was required to reorganize around and master the efficient use of this new technology. That's what he said in 1987. And then what happened is it finally took off in the mid-90s, right? It took off because we started to see that value. We started to see the idea of what it takes to bring this technology to make a business, or make a difference in our business and the way we work. And if you think about it, it's not just computer technology. The same thing was true with electricity. Electricity really didn't take off until we built the power grid. Automobiles. Cars really didn't transform in the way we think until we built the highway systems. So if you think about it, it wasn't just the light bulb. It was also the grid. It wasn't just the car. It was also the roads that make the difference. And I'm here today to say that it's not just the software, it's the integration and what's required to make all of this work. Because you've really got to think about how you put all the pieces together to get the true value out of this. And the reason I say this slide is quite interesting to me. It says 80% of you have a digital initiative underway. 69% say you must become more digital. Yet look at this, 44% are saying it's not making an impact to the bottom line. Maybe it's because we're in that paradox that was described earlier, that we've got to think about how we change and the way we leverage this technology and how we bring it together to make a difference in our business. And we believe one of those reasons is it's important to have a platform to build upon. And some of you have seen this before from us. I'll talk about it briefly, about what we describe as the platform. We've got this idea of ideation. It's the upfront phase of what we do, right? It's design, innovation, all of those types of things. Realization. You design it, somebody's got to manufacture and build it and produce it. Right? And then we've got a utilization phase, which is the feedback, or how you work and use with the, or how you work with the product that you've developed. Right? And the value of that is when we start to think about putting it together into a single digital thread. And how do you integrate these pieces together? And this is what we work on so aggressively at Siemens, to make sure we can bring all these pieces together. Because when we think about it, you've got to be able to represent all three, particularly if you talk about a digital twin, right? If a digital twin only represents ideation, are you really going to get to where you need to be? Because again, you've got to manufacture these things. You've got to figure out what's happening with the product in the field. How do you use it? And so we think those are extremely important. But the other part of the digital twin that's very valuable or necessary is to represent the multi-physics of the problem. I've got mechanical design, I've got electrical, I've got software. How do I bring all those pieces together? Because the value of the digital twin is how closely the virtual world can represent the physical. So how can you possibly represent the physical if you can't even represent electronics in the product? Or if you can't think about how you're going to manufacture it? And so that's why we spend so much time trying to make sure that we've got a comprehensive digital twin. And we think about that in a platform where we talk about the virtual product, production, real production, which is the automation running in the factory, and then the real product and the feedback loop back. And with the feedback loop, we're saying, look, what do we learn from this product? How do we bring that back into the digital twin and understand what's happening so we can make changes to our design and the way we work as we go forward with our product set? So I thought I'd take a moment just to walk you through what we mean when we talk about this idea of an integrated solution. This is one example of where you could be. Imagine you're in the truck business and you're losing market share. You're losing market share because your truck can't drive the same number of miles on a full tank of gas as the next truck. And so you're spending more time refueling. Marketing's coming back and saying, we've got to do something. Where are we at? And you really don't have time to redesign the entire truck. So you've got to think about how do I leverage the technology that I have today to quickly find a way to respond to this. So we look at extending the range, we look at our digital twin, and we say, well, what are some of the options I've got? One of the options might be a simple change is just change the size of the fuel tank, right? Because I can drive further because I've got more fuel. But what happens when I do that? Because it's a pretty complex system, right? If I want to analyze this, and I think about it through a systems-driven product development process, I want to start with that tank and then figure out what's all being impacted by the idea that I want to change this tank. So, in a systems model, I can go identify the tank and find everything associated with this. From this, I understand all the subsystems, the relationships, the requirements, everything associated with this design. So I can immediately understand what impact do I have in making this kind of a change. And then from that, because I've designed this through a systems model, I can put in a failure mode and effect analysis that kind of takes place automatically. It'll come back and tell me and say, look, based on the systems model you've designed, 9 times out of 10, we're going to predict in advance that your brackets are going to fail because they can't carry the load. From there then, we say, okay, well, what other things can we do? Well, first of all, using smart discovery, I can go in and identify this tank and say, I want to see everything associated with the fuel system, independent of what assemblies they're put in, independently of how everything's organized. I want to see the fuel system. Bring it to me so I can see what's going on. I want to see electrical. I want to see fuel. I want to see anything within a certain range of these components, regardless of how it's been organized in CAD and assemblies and so forth. And then, of course, I want to be able to do the design. You're going to hear a lot about what we're doing with NX over the next several days, and some of the things we're doing with convergent modeling and so forth that can change the way we think about design. From there, I take it into our CA tools with SimCenter and really start to understand what kind of problems I might have from an analytical point of view when I change the size of this tank. I can use shape search to go out and say, well, look, if I've got to design new brackets, maybe I've already got some brackets that exist in the company that I could leverage, and I search by shape and bring them to me. If I change the tank, I've got to change the line layout of the factory as to where I'm doing the work, the assembly process. If the tank's heavier, what kind of ergonomic issues am I going to have when I put this together? From there, I've got to create electronic work instructions or modify the work instructions that are being brought in place. I've got factory automation running the plant. How do I automatically generate the PLC code from the definition of what I've designed for my factory? so I don't have to have this handoff and intervention in between. Automatically generate the PLC code. And then I go into manufacturing operations management, implementing an MES, manufacturing execution system, to capture this. Back to IoT with our MindSphere solution. I want to capture data on the prototype of this as I put it together, because maybe I'm starting to see a vibration problem in the tank, and I've got these trucks all over the world in prototype phase. I feed it back up, the sensors off of the truck to the cloud, take that data, and I take real data from the truck, load it back into our CAE tools, and actually run CAE against the real data, vibration data, to understand what's going on versus what I predicted and what's really happening with the truck through an IoT feedback loop. And then from there, I can close out the loop even further to start looking at predictive type of issues that I might be seeing when I develop this type of a product. So this is a small example of some of the things. We have many areas you could go into as to what an integrated solution looks like. But I'm here today to give you some examples of how customers are already using this technology, and it's making a big difference in the way they go about their design and manufacturing process. Example here is Bugatti. Bugatti is, if you're not familiar, is one of the fastest production cars you can buy today. Very expensive car, by the way. But one of the issues they had was, if you think about a car like this, weight and drag are very, very important to the specifications of this car. One of the issues they dealt with was redesigning the spoiler on the back end. And the idea was, how do we take out some of the weight? How do we think about aerodynamics and so forth with the design of this product? So they came to us and they said, look, how can you help us? And so the first thing was looking at what we do with NX. And the idea of specifying requirements to feed into a generative design process, an organic design of a shape. From there then, if we get that shape, how do we manufacture it? Well, then we looked at what do we do with our additive manufacturing solution. Leveraging composites in the design, using what we've been able to provide for some time now within our composite capability. And then if I want to manufacture this and produce it through 3D printing, what I do with hybrid machining. Hybrid machining is interesting because every DMG Mori machine today that does hybrid machining ships with NX software, because they saw the value of how you could bring all this piece together. And so they looked at this, and what they were able to do was they developed a solution 10 times faster than their normal process, but also reduced the weight. If you see the picture on the left, you can see that the traditional design of the bracket holding the spoiler up on the right, traditional design, and then on the left you can see the kind of crazy looking shape. That shape is an organic design, part of it, the bottom half. The top half that sticks out of the vehicle as the vehicle's traveling down the road has very specific aerodynamic concerns that are modeled through our computational fluid dynamics solutions that we have. But they wanted to integrate the idea of faceted geometry through generative design, which you'll hear about a little bit later today, with traditional modeling techniques to be able to design that bracket, something we did very easily with them. And then the lower bracket is true organic design. You see the thing on the right, traditional design. We said, let the system design the software. In organic design, we give the loads, we give the constraints, we give keep out areas, and the software designs a part for us. And this is what they've leveraged to be able to reduce the weight to produce a solution that's 50% lighter than what they had before in their design process. Now, think about the transportation business. It's estimated there's over $1.5 trillion in cost inefficiencies in transportation today. $1.5 trillion. And what version Hyperloop 1 is doing is trying to find a way to eliminate that. So it's not just about building the Hyperloop, it's about everything associated with the Hyperloop and how you would think about travel. But these guys had a challenge. Their challenge was they had 1 year to come up with the prototype, and they only had 300 people. 300 people. Because oftentimes when I'm up here talking, we say, wow, we talk about the big companies, lots of dollars, lots of R&D, and so forth. These guys did it with 300 people. And what they did was they came to us and said, look, we need an integrated solution. We've got to take what we're doing with product design through NX. You've got to help us with computational fluid dynamics, and then how do we build a collaboration tool that we can go quickly with? Because again, even though we've got 300 people, we've got to do this within 1 year. By putting the solution together, They did it in 9 months. 9 months, 300 people to make this solution work, to get the first prototype built. The first prototype was 387 kilometers per hour in test. Again, you can achieve these types of things not by just throwing a bit of technology, but thinking about how do you put the solution together and how does it make a difference in the way you drive your business. Sometimes when I meet with customers, they'll tell me, you know what, it's easier for my design engineers to design a new part than find one that already exists. And this is kind of the problem that was happening at JCB. JCB is one of the top construction equipment manufacturing companies in the world. They do about 50 to 60 product launches a year. And out of those, they have over 200,000 variants. So quite complex when you think about that many variants to almost like an engineer to order. And what they were saying was their engineers were spending too much time trying to find parts they've already created. Close cousin, something very similar they could have leveraged. And they had to simplify the design process. They had to simplify the way they think about configuration. And so they came to us and they said, well, how do we integrate NX with this idea of shape search to find things and then a configuration tool to bring it all together? So we went there. We started by asking ask a few engineers to find 3 parts in 15 minutes. 3 parts in 15 minutes and all the data that they had for engineering. After 15 minutes, they found 0. Couldn't find any of them. So we put in shape search. In shape search, again, the idea is anything in your database is indexed by shape. Software automatically finds things similar and brings it to you. With shape search, the same thing, it took them 3 minutes. 3 minutes to find 3 parts. So previously, they couldn't find anything after 15. They found it in 3 minutes. The business impact of this. They reduced newly designed parts from 1 in 8 to now 1 in 20. A 2.5 times production improvement. Just being able to find what they've already got and be able to leverage it. And then use configuration capabilities so that they can make sure that when they're designing this, when they're laying out the configurations, using team-centered configuration, they know exactly what they've got. They're not violating the rules of configuration and eliminating the errors that they were working with before. So by leveraging this technology, major impacts to their business. Part of what you hear a lot about this week as well is the work we've already done with Mentor and the integration of what we're doing with our printed circuit board capability integration, integrated circuits, what we're doing there, some of the integration work we're doing with that to IoT and so forth. But in this particular case, it's really about design for manufacturability. It's how do you think about the idea of integrating printed circuit board manufacturing with manufacturing execution systems and IoT to think about how I go about the design of this. And you'll hear more about this later today as well, as to how customers are leveraging this. But what we're seeing is that with the closed loop approach, where we can monitor and understand where we're having failure rates or we have machine maintenance or other types of things that are occurring, through IoT we can get a feedback loop and make a tremendous difference with faster setup, just-in-time materials, better vendor selection based on what we're seeing. These are the integration pieces that you'll hear about a little bit later.
Utfordringen med å få unge I arbeid så stor at den ikke kan overlates til myndighetene alene. Flere bedrifter må nå ta mer samfunnsansvar, sier hotellkongen Petter Stordalen. Over 7 000 virksomhet eller utdanning.
Luckily, no one got hurt in that video. The reason no one got hurt is that for 2 years before that, Volvo Trucks was leveraging our pre-scan software to make sure that that emergency braking system acted and worked the way it was supposed to act. Hear a little bit about Volvo, what they're using.
As our active safety systems become more advanced, also our test methods have to become more advanced. And what we do here is basically that we can create any traffic scenario in the computer, and from the computer we get drive files that we then program our robots in the truck so that we can create the exact same scenario on the test track.
Yeah, the main components of the system is actually a main computer controlling all the systems. It's a steering robot and a robot controlling the acceleration pedal and the brake pedal, and then also a GPS unit that controls the location of the truck.
Right, I'm here with Robert, and so what's the deal now? What's about to happen?
Yeah, what we have done now is that we have programmed the robot in this truck and a truck in front of us that will do a scenario where we will follow the truck in front of us, and then there will be an obstacle on the road, testing the emergency brake.
And the truck is driving all by itself? I'm not doing anything?
No, what you should do only is to hold this button here, the dead man grip, that activates the robot. If you release that, then the robot will be deactivated.
Everything is set. You can start the test.
The test will soon start.
The reason why we do this are the increased accuracy and the repeatability, that we can create the exact scenario that we had in the computer on the test track, and we can repeat the same scenario over and over again with the exact same outcome. But also, if you want to vary a scenario, for instance, we want to change the speed or maybe the distance between the vehicles, this is also very easy to do, because we just change a parameter in the computer file, and then we program the robot and run a variation of the same scenario.
Okay, I will start the test in the laptop, activate the robot here, and then you can just go slightly forward, and then and then you can activate the robot. Yep, that's enough, and then you
now
press
push
the
this.
button. Yeah.
That's it?
Yep. Test started.
There we go. Oh,
Here we go.
Yeah. It's a bit awkward. The steering wheel is turning.
So now it will find the lane it should be located in, and just follow the truck in the front of us.
He's following the other robots.
He's following the other robots.
So now when that one turns out, does now, heavily, and I will just
hold tight. You can release the button.
I reached the button, yep.
It's estimated to get to Autonomous 5, no steering wheel, complete driving of the vehicle. It's estimated by Toyota, for example, the president of Toyota, it's going to require 8.8 billion miles of testing. Now, no one's going to drive 8.8 billion miles, right? So you've got to find a way to test and validate. The pre-scan software that you just saw in the example with Volvo is all about verification and validation of the algorithms and the software and the solutions to make sure the vehicle is going to act as you expect it to act. We looked at that. We said we could combine that with HEEDS for design optimization, where you iterate through so many cycles, along with DRS 360, which is a sensor fusion capability within vehicle. Sensor fusion is where you have to be in Autonomous 5, where you can't have all the sensors around the vehicle making decisions on their own. They've got to come back to a central CPU to be able to move quickly and make the decisions. We put those things together to be able to put an integrated solution. Back to what we said earlier, it's not just throwing technology, it's putting the pieces together so we can solve the 8.8 billion miles of testing to get to the level that allows us to have the trust that the thing's going to work the way you saw in the video previously for the stopping of the truck. And then in the area of the factory automation and the work we're doing, we've got a European automaker, for example, that had to validate the predictivity and the performance of their operations on the plant. And the idea was, how do I link the machine design to the line design to plant simulation to automation to our execution systems to a feedback loop, bringing all those pieces together. And what they're seeing is by being able to do this with our virtual commissioning capability, again, where we automatically generate the PLC code that drives the PLCs, and we can validate all of this through software. They were able to take the process that took them 24 weeks to do, 24 weeks down to 3. And so we talk a lot about disruption, and I've said before in events like this, in the area of disruption, you really have two choices. You're either going to be the disruptor, or you're going to be the person that responds to disruption very quickly. And you've got to have the solutions to be able to do that. And when someone's doing something 24 weeks versus 3, it's not long before disruption starts to occur. And that's why I think there's so much interest in the solutions that we provide through our digitalization piece, because it starts to make a tremendous business impact when you think about how you work. And then finally, in the area of IoT, we've got a heavy equipment manufacturer that the same thing, it's physical prototypes out in the field. Right? How do you gather all the data? By putting the sensors in place, IoT monitoring, our 1D simulation tools, collaboration tools, 3D simulation, and having a feedback loop so that when you have the product in the field, and you reach an overload condition, or back to the example I spoke about before, you got a vibration problem or whatever, right? You can get the digital twin feedback loop back to the product. And I would argue that Siemens is the only one that can bring that data back and leverage it in a comprehensive way to the digital twin. There's a lot of discussion about IoT, and IoT is really, there's a lot of work in the idea of preventive maintenance, condition monitoring, all those types of things. And that's extremely important. We at Siemens do that very well because many of the factories around the world have our equipment and we're already doing that. But we also took the same IoT piece to be able to leverage the feedback loop back so that you can bring it back to the digital twin and validate and verify and actually change the design. Rather than just telling me I might have a problem, I've got a heat condition or I've got a vibration problem. Rather than just telling me that, I can use the data to bring it back and make a change to the design as I go forward. And so in their case, they're seeing 40% reduction in test time, 20% cost savings. Again, very valuable feedback on this. So what does it take to make all of this happen? Well, this is what we talk about with a platform. We talk about our digital innovation platform. We bring all these pieces together to be able to put an integrated solution together to provide the solutions. Yes, we're still open, we still work with any other piece of software, but the most value comes we start putting pieces together to solve the problems, like you've seen through some of the examples that I've had. We did this starting back in 2007, where Siemens as a whole has invested since then over $10 billion into the software space. Most recently, as you know, the acquisition of Mentor. We have TAS for the pre-scan software, which you saw in autonomous vehicle. We've done 3 more acquisitions since then. 2 of those are in the integrated circuit space, 1 in motor design. So we've got a lot of areas where we continue to acquire and build out so that we can better build that relationship between the physical and the virtual world. So we have a more comprehensive coverage as to what we're doing. So what I would say is it's not about the software, it's about the integration. You're seeing companies already succeed with this. And we think this innovation platform is really the key of how you bring this all together, right? So I hope over this next few days you get a chance to really see some of this and really understand what it means to your business. But before we close it out, I want to just give you a few examples of what I hope you get a chance to look at over the next several days. First of all, Siemens as a whole, we have a corporate technology group that really looks at key technology areas. We've spent, I think last year, $6.3 billion in R&D in the area of automation, electrification, digitalization in these areas. And we as the PLM group leverage much of this because of the work that's being done in additive, for example, or autonomous robotics, simulation, digital twin. All of these pieces, not all, some like energy storage don't necessarily apply directly to us, but many of the pieces drive into what we're doing today. And what that's allowed us to do to start thinking about how we advance our technology, because when you got $6.3 billion of an R&D, it helps you do a lot of things much faster. So some of the things we're working on, and hopefully you get to see today, is in the area of Team Center. We looked at the UI, the response, and we're tweaking it one more time. We're making it much more easier, much more interactive. You'll see this as you go through the sessions this week. We've had a tremendous response to the change of the UI, making it much easier to use. In the area of virtual reality, we've done a lot of work here to leverage low-cost VR devices, so it's not this big expensive thing you have to go think about. And really, it's using the data as it is today, the way it's been prepped. You don't need to have data prepped. You can use it as is, and it's one button push, and I'm right into VR. Coming a little bit later this year, you'll see integrations of Team Center to Slack and Microsoft Teams as to promote the idea of better collaboration. We'll talk to you a little bit about what we're doing with this idea of a systems model, identify the component, see everything related to it, and how I get to the components that are there. Artificial intelligence, how do we take advantage of that? And we think about how we work. We've got things we're doing with part classification. One of the hardest things with part classification is somebody's got to go enter the data. And most times people don't want to do it. And so if we combine shape search with parts classification, we think we can make a big difference, similarly to what you saw before with JCB. And so Team Center is leveraging AI to automate that process. So you don't have to go through and put all the data in. We learn, we understand, and we're able to modify as to how we bring in data. You see more and more of that from us. In the area of multi-site, expanding and moving data around the world, Our next release will be 10 times faster than what we've previously done in moving data for collaboration. So a lot of great things there. In NX, you're going to see a lot about what we're doing with assembly load and performance. In version, in NX 12, we think we've got the best assembly load times of any product in the business as to how you look at large assemblies. We've got, I think our headline is wrong there. We've got the idea of integration that we did with Mentor Graphics for the increase, or the ability to bring together Expedition, Capital, and NX all into one tool set. You'll see the first examples of some of that this week. We've got the idea of what we're doing with convergent modeling, right? This is leveraging the idea of using facets in the design and generative design. We'll spend some time talking about with you. And then the idea of what we really talk about when we speak to additive manufacturing. Additive, I would argue, most people can model and print apart. That's not what additive is about. Additive is about how do you industrialize the process. And you've got to think about all phases of this process to get the true value out of it. So if you're thinking about, and you should be thinking about what's happening in additive, you really need to spend some time with us because we have a very different solution than just model and print. It's looking at the problem holistically as we think about this. And finally, I'll talk about our GEARS program. Our GEARS program was set up to have an online community for all of you to be able to communicate and share with each other as to what's going on. We've identified several individuals on the bottom here. These are the individuals that contributed the most to the online community to help all of you with the design problems you have when you think about the software and so forth. And so we've awarded the people mentioned here for being the top, and they've been automatically invited to this event. So we want to thank them for everything they've done with the community. If you're not part of the community, make sure you're taking advantage of it, because it can make a big difference. So with that, I just want to say I want to thank you for being here. We've got a lot to show you, and I truly believe we can make a big difference to the idea of how you address innovation in your company. Thank you very much.